So we go on to talk about open balls, neighborhoods, and local structure. Since we started to look at metric topology in the last video, there we saw metrics and distance functions, and we are able to establish how useful metrics can be in setting up the whole idea of open balls, which can lead to open sets, and then the whole idea of topological space. So we are progressing gradually into the core of topology. So here, still under metric topology, we are looking at open balls, neighborhoods, and local structure. So as we go on with that, we see the that in this lesson, of course, we develop one of the central ideas of metric topology, which is about local structure. So we will study open balls, closed balls, neighborhoods. Then we'll also look at the relationship between balls and neighborhoods. Then local structure of a metric space. Then how the choice of metric changes the geometry of balls. Then we'll take some worked examples as well as computational visualization with Python. So the key idea is that a metric tells us how to measure distance, and balls describe what it means for points to be close to one another. So metrics tell us to measure distance, and balls tell us how what it means for points to be close to one another. So once open balls are understood, many fundamental concepts of topology become natural like that. So, and that's why we consider things like neighborhoods and the rest. So let's go ahead and talk about open balls. I mean, the idea is not totally alien to us because while when we're looking at the whole idea of intuition, we studied open disk there, open and closed disk. So that's pretty close. So let X and D be a metric space. Of course, I think in the last video we learned that a metric space is the collection of a non-empty set and a metric, So this is a metric space. Now let X belong to X and R is greater than 0. That's the radius. So the open ball that is centered at X with radius R is defined by B sub D of X comma R, which is the collection of all Y belonging to the set X, such that the distance between X and Y is always less than the radius, like that. So in words, the open ball consists of all points whose distance from the center X is strictly less than R. So for an open ball, all the distance from the center of the ball is from this center of the ball, X is strictly less than the radius. So that is why it is an open ball. So less than is the strict thing here. So the three ingredients here, we have the center, we have the radius, and we have the metric determining distance. This metric, right, is determining distance. So the notion B sub D of X comma R emphasizes that the ball depends on the metric. So the ball, depending on metric D, centered at X, and the radius is R. So the open ball consists of all points whose distance from the center X is strictly less than R. So why is it called an open ball then? Why do we call it an open ball? The defining inequality is the fact that the metric is less than R. That's why it is an open ball. The boundary points satisfying distance between X and Y equals R here are excluded. So this strict definition of maybe in the case of a circle, for instance, this would be in second order, this would be a circle. So we exclude this particular part. Thus, an open ball contains its interior but does not contain its boundary. So in an open ball, the boundary is removed. So for example, I think the video, two videos before now, I think we're looking at how a circle is the boundary of a disk like that. So in an open ball, the circle is removed and we only have the disk left, the open disk. For example, in R with the usual metric, the distance between X and Y is the absolute value of X minus Y. So the open ball centered at 2 with radius 3 can then be defined as, so if this is the metric we have, right? The, the ball centered at 2 with radius 3 will simply be the given as the collection of all Y satisfying the fact that the absolute value of Y minus the center is less than the radius. Solving the inequality, we then have, anytime you have any expression like this, absolute value of Y minus 2 less than 3 means minus 3 is less than Y minus 2 less than 3. Then we solve each part. or we can just solve together. We add 2 to all the sides, so we have minus 3 plus 2, that's minus 1. 3 plus 2, we have 5. So y lies between minus 1 and 5. Therefore, we say that the ball centered at 2 with radius 3 is actually just the open interval minus 1 to 5 on the real line. So notice that minus 1 and 5 are not included. So it's that, so minus 1 and 5 are excluded. So like that. So B23 is actually the open interval minus 1 to 5 on the real line like that. So we see a connection between, that's why we had to look at real analysis before we got it as a foundation for topology. So let's talk about open balls in R. For the usual metric on R, which is the distance between X and Y, which is the absolute value of X minus Y, we have that the ball centered at X with radius R is a collection of all Y given R such that X minus Y is always less than R. This is exactly the open interval. So the open interval, so this is minus R, right? Less than X minus Y, less than R. So if we solve that, we have X minus R to X plus R that way. Therefore, the ball X comma R is simply X minus R plus X plus R. So the center minus the radius, the center plus the radius, you get the ball. So for example, the ball centered at 0 with radius R will simply be 0 minus 2 minus 2, 0 plus 2, 2. The ball centered at 3, whose radius is 1, will simply be 3 minus 1, 2, 3 plus 1, 4, easily. Then the ball centered at minus 4, whose radius is 2, will be minus 4 minus 2 minus 6, minus 4 plus 2 minus 2. Thus, on the real line, open balls are simply open intervals. So every open ball can be said to be an open interval in that sense. So let's talk about the membership in an open ball. So which elements belong to an open ball? Consider R with the usual metric. So determine whether 5 belongs to B2, 4. I mean, when we say the usual metric, we're talking about the distance function, the absolute value of X minus Y, basically. So determine whether 5 belongs to the ball 2, 4. So by definition, ball 2, 4 is, so by definition, right, 5 belongs to ball 2, 4. Well, how is that? Because ball 2, 4 itself would actually have to be 2 minus 4 minus 2, 2 plus 4, 6. So that's so the ball 2, 4 is actually on the number line, it is the open interval minus 6, minus 2. It is the open interval minus 2 to 6. So that means 5 automatically belongs to it. So 5 belongs to B2, 4. If and only if the absolute value of 5 minus 2 is less than 4. So, and the absolute value of 5 minus 2 is 3, less than, with 3, which is actually less than that 4. So we conclude that 5 belongs to the ball 2, 4. Of course, this is another way to approach it, right? That the distance between 5 and X must always be less than the radius. That's why we say it belongs. But the other way is you can take this ball now. So the approach based on what we've been doing. So since we know that a ball centered at X with radius R is the same thing as the open interval on the real line, X minus R, X plus R. So that means that the ball 2, 4 is simply the same thing as 2 minus 4, 2 plus 4. So that is minus 2, 6. And of course, 5 is here. So 5, since 5 is an element of minus 2, 6, then 5 also belongs to the ball 2, 4, like this. But this is another approach. The approach here is to look at the distance between that point and the center X. So the absolute value of 5 minus 2 is 3, and that is less than the radius 4. So we conclude that 5 belongs to the ball 2, 4. Now consider the point 6. If you consider 6 now, of course, my own approach will be, of course, based on this alone, we know that 6 is not included here. Though because this is an open interval, 6 it does not belong here, right? Although it is the upper boundary of the set, but it doesn't belong because it's an open interval. So 6 doesn't belong. But so the approach here is to find the absolute value between 6 and the center 2. So the absolute value is 4. So, and 4 is not less than 4. 4 is equal to 4 at worst, at best. So 4 is not less than 4. So that is false. Therefore, we say 6 does not belong to the ball 2, 4. So that's easy peasy because here 6 simply doesn't belong to the ball 2, comma 4 because it doesn't belong to the open interval minus 2, comma 6. So 6 appears there, but it is not. If it was a closed set, 6 would have been said to be part of that. So that's how that goes. Then this illustrates the importance of the strict inequality in the definition of an open ball. So that strict inequality is what makes a ball a ball. If we have an equality sign there, then it's no longer the kind it's no longer an open ball. It will be a closed ball, which we are going to see in a moment. Open balls in R2. Consider R2 equipped with the Euclidean metric D2 of x comma y. So the first one was in R1. That's the usual square root of x minus, I mean, absolute value of x minus y. But in Euclidean distance, we have square root of xy minus y1 squared plus x2 minus y2 squared. So if we let x be a comma b, that's the point a comma b, then we say the ball on that second metric now, x centered at x with radius r, is the collection of all y1s and y2s such that the square root of y1 minus a squared plus y2 minus b squared is always less than r. Equivalently, we have what looks like that area, the equation of an open disk. So you have y1 minus a squared plus y2 minus b squared less than r squared. Thus, in the Euclidean plane, an open ball is an open disk. So an open ball is an open disk in the Euclidean space, in the Euclidean plane, when we talk about R2, two-dimensional real number system. For example, the a ball, uh, so a ball with metric of order 2 at at center 0, 0 with radius 2 will simply be, in this case now, a is 0, y is 0, a is 0, b is 0. So y1 minus 0, y2 minus 0. So in short, we just have x squared plus y squared, and that is less than the square of the radius, which is 4. So this is the interior of the circle, x squared plus y squared equals 4. Because it is an open ball, this circle, which should have been its boundary, is excluded. So this is the interior of this circle, like that. Then we have an Euclidean. So talking about a Euclidean ball, consider B2 centered at 1, 2, comma 3. So a point xy belongs to this ball precisely when the square root of x minus 1 squared plus y minus 2 squared is always less than this radius. Is always less than this radius. So if we square both sides, now the square of this is transferred here. So we have so the ball for the metric 2 now at center 1 minus 1 comma 2 radius 3 is the collection of all xy such that x minus 1 squared plus y minus 2 squared is always less than 9. So the center is 2 and the radius is 3. So the boundary of the circle will simply be x minus y 1 squared plus y minus 2 squared equals 9. This is the boundary. So the boundary itself is not part of the open ball, and that is exactly why it is an open ball. So open balls depend on the metric. A very important point is that a ball is not determined only by its center and radius. It also depends on the metric, and that's why we usually write it like so. We have these two, whatever these two indicates the Euclidean, one indicates the Manhattan, and infinity indicates the maximum metric. So you need to understand the metric. So open balls depend on the metric. So we've seen the example of Manhattan and Euclidean before now. So a very important point is that a ball is not determined only by its center and radius. It also depends on the metric. On R2, consider three common metrics. We have the Euclidean metric, d2 of x comma y equals square root of x1 minus y1 squared plus x2 minus y2 squared. For Manhattan, we have d1 x comma y, which is absolute value of x1 minus y1 plus absolute value of x2 minus y2 for metric. So that idea of metric we saw in the last video is coming to play here. So for d infinity x comma y is the maximum of the absolute value of x1 minus y1, then x2 minus y2. Although these metrics measure distance differently, they all produce legitimate metric spaces. Consequently, the corresponding balls have different shapes. So, I mean, I think we also saw something like this in the last video. So these balls have different, depending on the metric, the same open ball with the same center and radius will have different shapes. So let's talk about the geometry of balls under different metrics. Consider balls centered at the origin with radius 1, right? So the origin also automatically tells us that A and B will be 0. So under the Euclidean metric, we have x squared plus y squared is less than 1. That's less than 1 squared, which is 1. So this will be a circular ball. The ball will be circular because it's more like the equation of a circle. except that the it is not equal to 1. Then under the Manhattan metric, we simply have the absolute value of x plus the absolute value of y less than 1. So in this case, now this will be so the ball is diamond shaped in this case because we have absolute value of x plus absolute value of y is less than 1. Under the maximum metric, then, so under the maximum metric, we have, okay, I guess we should be able to demonstrate this on Desmos. I suspect we should be able to do that on Desmos. So looking at the fact that x squared, x raised to power 2, x squared. Oh, what's happening? X, okay, squared plus y squared is less than 1. Okay, so you can see the circle, which is the origin, what is that called now? The boundary is not there. And on the other hand, if we have absolute value of x, so you see that's absolute value of x plus absolute value of y is now less than 1. So you see we also have this. So this is the for the Manhattan. Then lastly we have the maximum of absolute value of x and absolute value of y less than 1. So we have the maximum of absolute value of x, absolute value of y, and that is less than 1. So we have this rectangle. So all of them, they operate around the same axis like that. So, and you can see here, the Manhattan is always bigger as based on what we even saw before. Okay, we can take this. Okay. It's better to have it projected this way. So that's the deal going on there. And for all of them, so all the boundaries are not included. So you can demonstrate that on Desmos for sure. So the ball here is circular, the ball here is diamond shaped, and then the ball is diamond shaped because of course absolute value of x, it goes around this corner like this. And because it's less than 1, so you always have that moving all around that. And then for the maximum metric, it's the rectangle covering up everything. So now the maximum metric, the maximum of absolute x comma absolute y less than 1, which is equivalent to absolute value of x is less than 1 and absolute value of y is less than 1. Thus, B infinity at center 0. So you can see all of them, the center is 0 for all of them. The center is at 0. So, and that is minus 1, 1, and minus 1, 1 like that. So minus 1. So you have minus 1, 1, minus 1, 1 all around. So which is a square shape, which is square shaped. The important lesson is that the geometry of a ball is determined by the metric, not by the word ball itself. So the fact that it is a ball does not mean it will always be circular. That's what we learn from that now. So all these things we've done, just like all the things that demonstrated on Desmos, we can actually do in Python. For this Euclidean ball, you have xe, that's cos theta, ye sine theta. For Manhattan, so you have to concatenate 0, 1, 1, 0, 0 minus 1, minus 1, 0. And then then that's xm. For ym now, you have 1, 0, 0 minus 1, minus 1, 0, 0, 1. So you can see it's just a reversal and signs, reversal of order and signs for both. And then for the maximum ball metric now, we have x infinity, that's minus 1, 1, 1, minus 1, minus 1, then minus 1, minus 1, 1, 1, minus 1, like that. You just have a reversal and similarity at the point. So by the time you run all of this, you see what it all looks like. So you have the Euclidean metric, all with the center is always here, then the Manhattan, which is diamond shaped, and the rectangular shaped maximum metric like that. So, and you see the order of the sizes. So the maximum metric is bigger than the maximum metric is bigger than Euclidean. Euclidean is bigger than Manhattan. No, yeah, maximum Euclidean Manhattan like that. So let's talk about neighborhoods now, because the topic is open balls, neighborhoods, and local structure. So for neighborhoods, let the metric, let X comma D. So X is a set and D is the metric. So let X comma D be a metric space and let X be an element of the non-empty set X. So a set N, which is a subset of this original set X, is called a neighborhood of X if there exists some R greater than 0 such that the ball centered at X with radius R is actually a subset of the whole N. So for instance, we've already seen that, I mean, in some sense, the ball centered at X with radius R can be an interval, an open interval on the number line. So if that number line is now a subset, if that interval is now a subset of this other set N, then we say that that N is a neighborhood of X in that sense. So in words, we say that a neighborhood of X is a set that contains some open ball centered at X. Okay? A neighborhood of X is a set that contains some open ball centered at X. So, from what we know about about so let's imagine that we have a ball. Let's say this is a ball like this. I mean, just in the rough sense of the word. So a neighborhood of this now, of B. So this is our B here. This is the ball. So a neighborhood of this will be another set that is centered at the same place like that. And B is a subset, or they can actually even coincide like that. So a neighborhood of X is a set that contains some open ball centered at X. This definition is extremely important. A neighborhood does not necessarily have to be an open set. It may not be an open set itself. It only needs to contain an open ball around the point. So let's talk about neighborhood versus open ball now. An open ball is always a neighborhood of its center. An open ball is always a neighborhood of its center. Indeed, the ball centered at X with so a ball is, in short, is always a subset of itself. That's what we are saying. So the defining condition for being a neighborhood is satisfied in that case. However, a neighborhood can be much larger than an open ball, just like what I gave here. So this neighborhood here is larger than open ball. The key thing is that they are centered, they have the same center basically. So for example, in the real number line now, N, which is the closed interval -1 to 5, including -1 and 5, is a neighborhood of 2. So N is a neighborhood of 2 in the sense that, and why is that? Because if we have a ball 2, 1, for instance, so on the real number line, that will be 2 minus 1, 1, 2 plus 1, that's 3. So, and we see that this 1, 3 now is a subset of this N. So in that case now, we can say that this N is a neighborhood of 2 because because it contains 2 in it like that. And 1, 3, 1, 3. This we see that B, which is 2, 1, is 1, 3 on the ball centered at 2 with radius 1 is the open interval 1, 3 on the real number line. And 1, 3 is a subset of -1, 5 like that. Therefore, we say that -1, 5 is a neighborhood of 2 because, I mean, focusing on the center. So -1, 5 is a neighborhood of 2. So, and that is because 2 lies somewhere in between there. Now that -1, 5 is not open, I mean, though -1, 5 is not open, it doesn't change the fact that it's still a neighborhood of 2 like that. So we have that. Thus, we say neighborhood is not equal to necessarily open set. So a neighborhood does not have to be an open set, although we are talking about an open ball, right? So how do we identify neighborhoods? Consider R with its usual metric. Determine whether the following are neighborhoods of 0. So how do you know it's a neighborhood of 0? It means for a ball centered at 0 with whatever radius, right? You now want to see. So imagine set 1. Set 1 is the open interval -2 to 3. So since the ball is centered at 0, 1, it can be easily said to be 0, 0 minus 1 minus 1, 0 plus 1, 1. So, and this -1 minus 1 is lying somewhere in between -2 and 3. So it is a subset of -2 and 3. So in that case, we say that N1 is a neighborhood of 0. So that's one there. Then imagine set 2 now. For set 2, we have N2, which is -1 and 2. Is this actually a neighborhood of this one? So if we have a ball with center 0 and radius half, for instance. 0 minus half is minus half. 0 plus half is half. And this minus half, half lies somewhere in between. It lies somewhere in between minus 1 and 1, though a closed set, a closed interval. So it's minus half half is a subset of the closed interval minus 1, 2. Therefore, again, n2 is also a neighborhood of 0. It's a neighborhood of 0. Now, looking at set 3, that's the open interval, the closed interval 0, 2. So no open ball centered at 0. So in this case now, no open ball centered at 0 can be contained in 0, 2, because every ball around 0 contains negative numbers. All right? Because every ball around 0 contains negative numbers. So once the center is 0, right? The all the other neighbors will have to be because whatever you now have as radius, a radius has to be positive always, like that. So 0 minus r will be negative, and 0 plus r may be positive or negative still. So in that case, no open ball centered at 0 can be contained in 0, 2, because there's no negativity here. And for any ball centered at 0, you have to have a negative value surrounding it. So no open ball centered at 0 can be contained in 0, 2, because every ball around 0 contains negative numbers. Therefore, N3 is not a neighborhood of 0. This example shows that the location of the point inside the set matters. So the location really matters. So, I mean, imagine there's no ball you can imagine that is centered at 0 that won't have a negative value surrounding it. Imagine 0, 0, let's say 0r, generally speaking. That will always be on the real number line. That'll be 0 minus r, 0 plus r, like that. That'll be the interval on the real number line. So that's minus r plus r. And of course, r is radius, so it is always positive. So we have minus r, r. So whatever r is, it must be this. So there's no way. So this is always, I mean, we know R is always greater than 0. That one is settled. As a result of that, so B centered at 0 with whatever radius can never be a subset of the closed interval 0, 2, because this one, okay, let's put it this way. Beta centered at 0 of R is always equal to minus R, R, and this will never be a subset of the closed interval 0, 2, because I mean we have negative sign here, so the negative value doesn't lie anywhere here. So in that case, this is not a neighborhood, neighborhood, not neighborhood. So that's the idea there. So you have to test that to see. So characterizing neighborhoods then, for a metric space x comma d, a set n is a neighborhood of x exactly when there exists a radius r greater than 0, such that the ball centered at x with radius r is a subset of n. This is where this one actually breaks down, because minus r can never be a subset of 0r, because this is negative here and this one is starting from positive side, so it can never be a subset like that. So for a metric space xd, a set n is a neighborhood of x exactly when there exists a radius greater than 0. Of course, radius is always greater than 0, such that the ball centered at x with radius r is a subset of the neighborhood n. Equivalently, we say that x belongs to n naught. X belongs to n naught, where n naught denotes the interior of n. So x belongs to the interior of n. So in this case now, the x here does not belong to the interior. So in this case, x does not belong to the interior of n here, like that. So thus n is a neighborhood of x if and only if x is an interior of n naught, and if x is an interior of n naught, then n is a neighborhood of x. This connects neighborhoods directly to the concept of interior. In fact, the collection of all neighborhoods of a point describes the local behavior of the space around that point. The collection of all neighborhoods of a point describes the local behavior of the space around that point. So let's talk about closed balls. Of course, since we know that the remarkable thing about open ball is the fact that we have whatever the metric is defined as, it's always less than, or strictly less than, the radius. So when equality sets in, then we have a closed ball simply. So the closed ball centered at x with radius r is defined by b bar x comma r, which is the collection of all y belonging to x, such that d of x comma y is always less than or equal to r. So it's a closed ball because of the equality. So the difference between an open ball and a closed ball is just the inequality. So b of x r, so less than r for closed ball, for open ball, whereas for closed ball, we have less than or equal to. So this closed ball therefore contains the boundary. So basically, the closed ball contains the boundary, while the open ball doesn't contain the boundary. And the boundary is actually the circle, because at that point, the radius, if we're talking about it in terms of, uh, uh, R2 now. So the closed ball therefore contains the boundary in R now. So we have the closed ball, um, the closed ball XR will now be, instead of open interval like before, we have closed interval x minus r to x plus r. Same limits, but then this is now closed. So x minus r and x plus r are included. For example, the closed ball 2, 3 is simply 2 minus 3 minus 1, 2 plus 3, 5. So, and minus 1 and 5 are included in the closed ball. So open ball versus closed ball now. For every metric space, the open ball is always a subset of the closed ball. I mean, for obvious reasons, because in addition to everything, the open ball has, the closed ball also has the boundary, which is the circle or whatever that might be. So the difference is that the open ball excludes points satisfying the fact that the metric is equal to the radius exactly, while the closed ball includes them. For example, in R, the ball 0, 2, the ball 0, 2 is minus 2, 2, whereas the open ball 0, 2 is minus 2, 2, and the closed ball 0, 2 is minus 2, 2, a closed interval. So the open ball 0, 2 is the open interval minus 2, 2, while the closed ball 0, 2 is closed interval minus 2, 2. So here, minus 2 and 2 are included for the closed ball. Minus 2 and 2 are not included for the open ball. Thus, we say that minus 2, 2 are, are, uh, are not elements of the open ball, whereas minus 2, 2 are elements of the closed ball. Very interesting idea to note. It's very simple, but it's easy to stumble on it. So important warning about closed balls now. A closed ball is not necessarily a closed set in every topological context, unless the relevant metric structure is being used. So you need to know the metric you're working with. So for a metric space, however, every closed ball is actually every collection of y such that the metric is always less than or equal to r. So we say it is closed. So every closed ball B like that is closed. To see why, consider a point Z outside a closed ball. Then we see that the metric is greater than R. So if you set epsilon to something like the metric, since the metric is greater than R, so we have the metric minus R to be greater than 0 then. So if the distance between z and y is less than epsilon, then by triangle inequality, we see that the distance between x and z is less than or equal to the distance between x and y plus the distance between y and z. Hence, the distance between x and y is greater automatically than the distance between x and z minus the distance between z and y, which is greater than the distance between x and z minus epsilon, which is r. Therefore, points sufficiently close to z remain outside the closed ball, no matter how close they are. So they will remain outside because the closed ball has it will exclude every other point. Thus, the complement of the closed ball is open. So the closed ball is closed. So if the complement of the closed ball is open, then the closed ball is always closed. So let's talk about open and closed balls in 2 dimensions. Consider the point x, which is 2 comma minus 1, and the radius r is 2. So the open ball B2 or naturally will be the center that's 2 comma minus 1, and the radius is 2. So you have y1 minus 2 squared plus y2 plus 1 squared, which is less than 4. That's the open ball. Of course, the closed ball will just be same thing for, but then less than or equal to 4. That equality makes the difference. So the boundary y1 minus 2 squared plus y2 plus 1 squared is equal to 4. So the open ball contains points strictly inside the circle. The closed ball contains both the interior and the circle itself. So the boundary and everything are involved. So every open ball is actually open. One of the fundamental properties of metric spaces is that every open ball is an open set. So if it's an open ball, then it's an open set. Let the ball centered at x with radius r be an open ball and choose y, which is y to be an element in the ball x comma r. Then the distance, the distance between x and y is simply less than the radius. And then if we define epsilon, to be r minus dxy, right? So yeah, so taking it that the metric is less than r. So since the distance between x and y is less than the radius, then epsilon is greater than 0 in that case. Then we claim that the ball centered at y with radius epsilon is a subset of the ball centered at x with radius r. So this new one now is like right inside the normal ball we define. So if you take any z belonging to the ball centered at y with radius epsilon, then the distance between y and z is always less than this epsilon. By the triangle inequality, now we say that the distance between x and z is less than or equal to the distance between x and y plus the distance between y and z. Therefore, the distance between x and z is less than the distance between x and y plus epsilon, which is equal to the distance between x and y plus r minus the distance between x and y, which is equal to r, simply because this cancels out and you have r here. Hence, Z being an element of the ball centered at x with radius r, therefore, the ball centered at y with radius epsilon is a subset of the ball centered at x with radius r. That's the open ball, both of them open balls, which proves that the open ball is open. So every open ball is an open set. That's the proof for that. So you may want to sit with that to really get the flow. The key local property of open sets now. The previous result gives an important characterization. A subset U of X is open if and only if for every point X belonging to U, there exists a radius R such that the open ball B centered at X with radius R is an open set. I mean, is a subset of that U. Thus, U is open if and only if there exists a particular X in U such that sorry, U is open if and only if for all x belonging to U, there exists a radius r such that the open ball B centered at x with radius r is a subset of U. So this is one of the most important bridges between metric spaces and topology. So an open set is a set in which every point has some room around it that remains inside the set. So an open set is a set in which every point has some room around it that remains inside the set. So then we go on to talk about the idea of local structure. The phrase local structure refers to what the space looks like near a particular point. So for a point x belonging to x, we can examine smaller and smaller balls. Say we have the open ball B centered at x with radius r. As r approaches 0 plus, as the radius becomes smaller, these balls reveal the immediate environment of x. So the collection of balls such that r is greater than 0 is called the neighborhood basis or local basis at x. I think I demonstrated something like that in the video yesterday, where I showed how the circle inside a disk, keeps shrinking until it disappears into the center like that. So here, this gives an idea. So the collection of balls such that the radius is always greater than 0 is called the neighborhood basis or local basis at x. So it is enough to understand these balls to determine many local topological properties. For example, to determine whether x is an interior point of a set A, we ask, there exist some radius r greater than 0 such that the entire ball B, which centered at x with radius r, lies inside A. So that takes us to the idea of interior points and local structure. So I know we're still going to talk about this more as we go on, I believe. So let A be a subset of X. So a point X belonging to A is called an interior point of A if there exists a radius R such that the ball centered at X with radius R is a subset of A. So uh, uh it's more like it's a bit close to the idea of neighborhood we also saw the other time. So if a point X that belongs to a set A, which is a subset of X, a point X belonging to A, which is a subset of X, is called an interior point of A if there exists a radius greater than 0 such that the ball centered at X with radius R is a subset of A. So the set of all interior points is called the interior of A. The set of all interior points is called the interior of A, and that is denoted by A degree also. Therefore, A degree is the collection of all x belonging to A, such that the radius greater than 0 for the ball B of x, comma r is always a subset of A. So this definition is fundamentally local. Whether x is an interior point depends only on what happens sufficiently close to x. For example, for A now, which is the closed interval 0, 1, of course, that is a subset of the real number line. Every point in the open interval 0, 1. So this is a closed interval now. But every point in the open interval, of course, this open interval is a subset of this closed interval. So every point here is an interior point like that because this is basically a subset of A. However, 0 and 1 are not interior points because every open ball around either endpoint contains points inside 0, 1 because 0 and 1 are not part of this now. Hence, 0, 1 prime is 0, 1. So the interior of a closed interval is simply the open interval, basically. So the interior of a closed interval is the open interval. The interior of the closed interval 0 to 1 is the open interval 0, 1. So we have a local test for membership in an open set. Suppose we want to determine whether a set U is open. Instead of analyzing the entire set at once, we can test each point locally. For every X belonging to U, we ask whether there exists an R greater than 0 such that the ball is a subset of U. So if the answer is yes for every point, then U is open. For example, if U is the open interval 0, 5, if you take any X in this interval 0, 5, any value at all, maybe any number, but if you even focus on integers like 1, 2, 3, 4. So take any of them. So a valid choice is R, which is the minimum between X and 5 minus X, for instance. So since X is greater than 0 and 5 minus X is also greater than 0, then we have that R is greater than 0. Then we can say that the ball X centered at X, the ball B centered at X with radius R is always a subset of U here, of this 0, 5. And therefore, we can say that 0, 5 is open. 0, 5 is open on the real number line. So it's open. So finding a suitable radius now, consider U is 1, 10 and the point X is 4. So we want to find R greater than 0 such that the ball 4, R is a subset of 1, 10. So the distance from 4 to the left point, the distance from 4 to the left point here, 4 minus 1 is 3. And the distance from 4 to the right point, that is 4, that is 10 minus 4, that is 6 here. So in that case now, based on what we have like that, so 4 minus 1 is 3, 4 minus 10 is 6. Therefore, any radius satisfying, any radius lying between 0 less than or equal to R less than or equal to 3 will work in this case. So we take the smaller one. We take the smaller one. We don't take the bigger one. So this actually was, for example, if you choose R to be 3, so for R, any value of R that is bigger than 0, but bigger than 0 all the way to 3, will work in that situation. So for example, if you choose R to be 2, which lies in this interval, then the ball 4, 2, because R is 2 now, the ball 4, 2 will just be 4 minus 2 to 4 plus 2, 6 in that case. And 2, 6 is actually a subset of 1, 10, as we see. So 2, 6 is a subset of 1, 10. Even 3 can work, right? So 4, 3, that will be 4 minus 3, 1, 4 plus 3, 7. So 3, 7 also lies within that interval. Thus, 4 is an interior point. We see that 4 is an interior point of 1, 10, like that. So the focus is on the X and that other set. So the radius of locality now, for a point X in a set A, the size of the largest border can fit inside A around X provides useful information about how deeply X lies inside A. For example, if A is the open interval 0 to 10 and X is 4, so then the distance from X to the boundary of A will be the minimum between 4 and 6. That's 4 minus 0, 4, 4 minus 10, 6. So the distance from X to the boundary of A is the minimum between 4 and 6, which is 4 here. Thus, every ball B, at 4, every ball B centered at 4 with radius R, uh, thus every ball B centered at 4 with radius R with radius starting from 0 to 4. I mean, not starting from 0, bigger than 0, but up to 4, 0, 1, anything from 0 upwards is contained in A like that. So at the endpoint, X is equal to 0, at the endpoint, X is equal to 0. However, no positive radius works. So, um, That's at the endpoint. So this illustrates the difference between an interior point and a boundary point. So boundary point and interior point works there. So the radius of locality. So open balls form a basis for metric topology. So the collection of all open balls, that is all B's, such which is the collection of all open balls for x belonging to x and r greater than 0, forms a basis for the topology induced by the metric. So put all the balls together. The collection of all of these open balls will form a basis for the topology induced by the metric. This means that every open set can be constructed from open balls. So more precisely, if U is open and X belongs to U, then there exists an open ball B centered at X with radius, right? Such that X is an element of the open ball, and the open ball itself being an element is a subset of U. Consequently, the set U can then be the union of all the open balls like that. So for suitable choices of radii, Rx greater than 0 in this case. So thus, metric topology can be viewed as a topology generated by open balls. So metric topology is a topology generated by open balls. So we go ahead to talk about local structure and topology. The concept of local structure is fundamental because many topological properties can be expressed in terms of neighborhoods. For example, X is an interior point of A if some ball around X lies inside A. We saw that a lot. X is a boundary point of A if every ball around X intersects both A and its complement. Then X is a limit point of A if every ball around X contains a point of A different from X. A is open if every point of A has a ball contained in A. Then A is closed if its complement is open. Thus, open balls provide the basic language for describing local behavior. So talking about boundary points now, consider A, which is the closed interval 0, 1, which is a subset of the real line. Take the point x equals 0. So every open ball around 0 has the form B0, B0, comma R, which is 0 minus R minus R, 0 plus R, R. So this ball contains points of A such that as 0 and points outside A, such as 0. So this ball contains points of A, such as 0, and points outside A, such as minus R over 2. Therefore, every neighborhood of 0 intersects both with A and X take away A. So hence, 0 is a boundary point in this case. The same reasoning applies to 1. Thus, the boundary of A will be 0, comma 1 in that case, based on the fact that we have A here. So in contrast, points such as half are interior points in that case. So half is located somewhere there. Then let's talk about open balls in general metric spaces. The definition of an open ball does not require coordinates. So let X be any metric space. This is a set and a metric. So for X belonging to X and radius belonging greater than 0, so we have the open ball, which is the metric less than R, you know. This applies to many different spaces, like the one-dimensional real number, n-dimensional real number, spaces of functions, spaces of sequences, spaces of matrices, discrete sets, finite metric spaces, spaces arising in data science and machine learning. The metric tells us what close means, and the ball records the points that are close enough to the center. So then we talk about the discrete metric now. We talked about discrete metric in the last video. The discrete metric is defined as follows. Let X be any set and define the discrete matrix XY to be 0 when X is equal to Y, 1 when X is not equal to Y. This is called the discrete metric. So consider a ball of radius R less than 1. So for Y not equal to X, the distance between X and Y will always be 1, which is greater than the radius because R is less than 1. Therefore, the only point satisfying the distance, the distance between X and Y less than R is X itself. This X itself. Hence, the ball centered at X, comma R is the collection of all X, like that for every R ranging for every R between 0 and 1. This is just the X itself. Thus, the local structure of the discrete metric space is extremely fine. It's very tiny because it's just the center itself. So every individual point has a singleton neighborhood. This is very different from the usual geometry of R. So for a discrete metric, we have a special behavior of a ball like that. The ball is just the collection of all X's, which is basically the center of the ball. So talking about the maximum metric then, consider R2. The maximum metric simply talks about the biggest of x1 y minus y1 and x2 minus y2 absolutes, right? The open ball centered at the origin with radius r can then be uh you know this 0 comma r, and then we take the maximum of x and y because this is the center is 0 in the first place, so which is less than r. So this means that the absolute value of x and the absolute value of x is less than r, and the absolute value of y is also less than r. Therefore, the ball centered at 0 with radius r is minus r by minus r like that. So the ball is an open square. That's why it's an open square, like we demonstrated here previously. So for this green one out here, so it's an open square. So the same underlying set r squared can therefore have dramatically different looking balls depending on the metric. Depending on the metric. So, uh, of course, we've seen this before. So so it's the same code. I think we've seen this before. So I'll just, see the Euclidean ball, the Manhattan ball, and the metric ball. Exactly what was shown here too. So why does local structure matter? Why local structure matters? Um, the idea of local structure appears throughout mathematics. In calculus, we study how functions behave near a point. Then in differential equations, we study local existence and behavior of solutions. In geometry, we ask what a space looks like near a point. In topology, we study properties preserved under continuous deformation. In analysis, neighborhoods describe convergence and continuity. In machine learning, distance functions and neighborhoods appear in clustering, nearest neighbor methods, anomaly detection, and manifold learning. Thus, open balls as such are much more than a technical definition. They provide a mathematical language for closeness and local behavior. That then let's talk about open balls and continuity. The notion of continuity can also be described using neighborhoods. So suppose F maps two metric spaces with sets x and y and metrics dx dy. So and x naught belong to x. So the function f is continuous at x naught if for every epsilon greater than 0 there exists delta greater than 0 such that the metric over x for talking about the distance between x and x naught is less than delta implies that the metrics over y for the distance between f of x and f of x naught is less than epsilon. So it's more like the continuity we have in calculus, but in the sense of metrics now. So using balls, this becomes f, the ball defined over x, the ball with matrix x for x naught and d, being a subset of the ball defined on y for f of x naught and epsilon like that. So this is another local statement. So points sufficiently close to x naught are mapped to points sufficiently close to f of x naught. Thus, the language of balls naturally leads to continuity. So a useful mental picture to capture the whole idea. When working with metric spaces, imagine placing a small bubble around every point. So every point you talk about, there's a small bubble around it, right? Say say every point, and you have some bubble around that point. So if we assume that, so the bubble is that ball now. So that ball contains the point. So the bubble is the ball centered at x with radius r. So the metric determines the shape of the bubble. So it could be circle, it could be diamond, it could be rectangle, depending on whether it is Manhattan, Euclidean, or maximum distance. So the radius determines how large it is. So the bubble could be bigger than so the bubble could be even bigger than what I have here. So it all depends on the radius in that case. So as R moves towards 0 from the positive side, the bubble shrinks towards its center. So the local topology is encoded by which sets contain sufficiently small bubbles around their points. So this picture is especially useful when thinking about open sets, neighborhoods, interiors, boundaries, continuity, convergence, local compactness, and local connectedness, which we still get to study very well under topology. So in summary, we have seen some definitions. The central definitions are for an open ball, you have the ball centered at x with radius r is a collection of all y belonging to x such that the distance between x and y is always less than r. Less than r, that's what makes it open. It is closed, so we now have a closed ball when we have equal to r because now this one contains all the points here with where a radius when the matrix is equal to the radius itself. Therefore, neighborhood, we said a set N is a neighborhood of X if there exists a radius greater than 0 such that the ball is a subset of N. Then we have interior point, a point X, which belongs to A, is an interior point if there exists a radius R greater than 0 such that the ball is a subset of A. Then we say that X is an interior point. Then we have the local base. So the family of balls for radius greater than 0 forms a neighborhood basis at X. So the fundamental principle now leads us from metrics to distances, to balls, to neighborhoods, and then we enter into topology. Understanding this chain is essential for understanding metric topology, which this subsection is about. So some key takeaways: an open ball contains all points strictly closer than its radius. Then a closed ball contains all points whose distance is less than or equal to its radius. So open balls depend on the chosen metric. A neighborhood of a point contains at least one open ball around that point. Every open ball is an open set. A set is open precisely when every one of its points contains an open ball lying entirely inside the set. Open balls form a basis for the topology induced by a metric. Then local structure describes how a metric space behaves near individual points. Different metrics can produce very different geometric shapes for balls, like we've seen already. Euclidean, the Euclidean is given like a circle. Manhattan gives like a rectangle, while no, maximum gives a rectangle, and Manhattan gives that diamond thing, which we demonstrated here. So this is Euclidean. We have the circle. This is Manhattan, which is the blue, this one, this diamond, and then the maximum, this is Manhattan. So Euclidean, circle, then diamond, Manhattan, then maximum. Yeah, maximum is the green one, like that. So the concept of interior boundary, continuity, and convergence are all closely connected to neighborhood and open balls, like that. So the final perspective. So the transition from distance to topology is one of the most beautiful ideas in analysis. So a metric begins with a numerical question. How far apart are X and Y? Open balls transform this numerical notion into geometry. Which points are close to X? So that talks about open balls. Then neighborhoods then transform this geometry into topology. What does the space look like near X? Then this local viewpoint is the foundation for much of modern analysis and topology. So once we understand open balls and neighborhoods, the abstract language of open sets, closed sets, continuity, convergence, interiors, boundaries, and limit points becomes much more intuitive. Yeah, because of the time, I think I won't be able to take to solve any questions, but you can just follow the ideas we've been working with. So you have questions up to question 1 to 6, all clear here. And here you have you can see all of 6 to 10. Okay, let's say 6 to 12. You see all of 6 to 12 here. Then 13 to 18. In case you try your hands on anyone and you think you still need help, you can let me know. So I may make a separate short video just to solve whatever problem you may be interested in. Then we have the rest. Let me know how helpful this is for you. And if there's something else let me try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, this is a very good time to go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you special privileges you will find when you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.